Well, good morning, everybody. And I've had a chat with a few folks, and you're all bright-eyed and bushy-tailed, so nobody stayed too late at the reception last night. I understand my institute were the people who closed it down. Be careful, guys, okay? I think we had a great day yesterday, and I've got to thank yesterday both Ruth Onyango and Gary Stacey for really getting this off to a fantastic start. And I think yesterday's debate in the afternoon could not have gone better. I thought it was a paradigm of rationality, and I've just got to take my hats off to all the speakers. What a great job you did. Thank you so much. We've had so much feedback from the outside world who were watching this in a live feed. We've had a lot of comments, and in fact, if anybody's interested in the Twitter sphere, we actually trended to #1 yesterday, so something good was happening. So with that kind of momentum behind us, we're really looking forward to today's deliberations, and we will get into some very solid science and solid international development discussions. And I'm going to hand over now to Professor Bruce Coleman. Bruce is a professor in our plant sciences department here at the University of Saskatchewan, but he's also the chair of the IITA in Nigeria, in Africa. And he's going to now officiate for the first two talks this morning. Let me just say a big thank you as well. We've had nice coffee and starters here this morning. That was provided.
And they will each have 45 minutes for their presentations. I received some advance warning that both of these gentlemen are very loquacious. However, they have guaranteed that they will not take the full 45 minutes and will allow us some time for questions. So our first speaker is Dr. Ratan Lal. And Dr. Lal is a distinguished university professor of soil science and director of the Carbon Management and Sequestration Center at The Ohio State University. Earlier in his career, Dr. Lal spent 18 years as a soil scientist at the IITA campus in Ibadan, Nigeria. Dr. Lal has received honorary degrees from 4 international universities. He has been president of 4 international organizations, and he was cited in the Thomson Reuters 2014 and 2015 list of the world's most influential scientific minds. Over his career, he's mentored more than 100 graduate students, around 50 postdoctoral researchers, and has hosted close to 150 visiting scholars from around the world. He has authored or co-authored close to 800 scientific, refereed scientific journal articles, and he's written himself 19 books, and he's edited or co-edited another 63 books. So we're very pleased this morning that we have Dr. Lal as one of our plenary speakers, and his presentation is going to be on soils.
IITA. I'm going to begin with showing you some pictures from my hometown, family going on outing. I won't repeat the exact numbers here, but a few numbers of population global are important. Current population 7.4 billion, 2050 9.7 billion, 2100 11.2 billion. Over the last 10,000 years, the number of humans has increased about 1,000-fold, from 20 million to about 7.4 billion now. And their impact is given by PAT, P population, A affluence, T technology. We're going to talk about the impact of this population. Another spiral I'd like to show you is from another hometown, Ibadan, and the population spiral for sub-Saharan Africa, beginning to a very humble number of less than 0.1 billion, and ending up by 2020 to 1.1 billion, 2050 to 2.1 billion, 2,100 to almost 4 billion. And impact of that one, of course, is the same, much greater, both on the environment and on the natural resources. One example, in year one, we had 188 million population, cropland area 130 million hectare, pastoral land 110. By 1800, population about 1 billion, 420 million cropland, 510 pastoral land. At present, population of 7 billion, about 1,400 million cropland, 3,500 million pasture land, irrigated area, almost 300 million hectare. Global fertilizer use tremendously increasing between 50 and 2012, for example. By 2050, the fertilizer consumption of nitrogen goes from 10 million tons a year to about 236. Yesterday's excellent talk on nitrogen fixation might help some. Phosphorus goes up from 10 to about 83 by a factor of 8. That's quite serious because I have very limited resource. Potassium, and of course the total fertilizer, quite a large number. Similarly, the pesticide use worldwide, about 2 million tons per year. Europe consumes 45%, US 25%, herbicides almost 50%, and others, quite a lot of input of chemicals. Consequently, the cereal yield, as you expect, have gone up linearly. Unfortunately, the per capita has not. In fact, over the last 20 years, it's decreasing. I will show you another image of that. But in terms of the impact, which I'm interested in, let's talk about the human population scenario for a moment. Population 2015, 7.3 billion. We have already a figure of 9.7 and 11.2. As a result of that, of course, soil degradation, erosion, a very serious issue affecting, especially in sub-Saharan Africa and Nigeria. I used to monitor sometime 80 tons per hectare per year at IITA, affecting about 1.1 billion hectare by water, 0.6 billion hectare by wind. Secondary salinization. This is from Faisalabad, Pakistan, irrigated area. Same problems exist many other parts of the world. 20% of all irrigated land is already affected by secondary salinization. That's another hometown picture from Ohio. The algal blooms affected by the impact of chemicals, eutrophication, the Great Lakes. You remember Toledo, what happened a couple of summers ago, 4 days, no drinking water. The urbanization problems, considerable, serious. By 2030, global urban land will increase by 152 million hectares, that's 10% of the total cropland area of the world at the moment. The loss of species as a result of that, the rate at which the species are lost, 1,000 to 10,000 species per year compared with a background rate of only 5. Deforestation. I was there very recently. At current rate of about 9 million hectares per year, 7 million hectares in 2000, the size of Sri Lanka is deforested every year. The water aquifer, especially the Indus Valley, the Punjab, Haryana, and Rajasthan area, losing more than a meter a year. The North China Plain, the Ogallala aquifer, draining, depleting very rapidly indeed. And of course, the emission of greenhouse gases, which is tremendous in terms of deforestation, which is about 1 billion ton of carbon per year, the fossil fuel about 10 billion. But the number I'd like you to think about for a moment is 500 million ton, 500 gigaton, 486. Land use, conversion, has contributed carbon into the environment, out of which the soil is about 80 to 100. Those two numbers are critical because we, through management, recarbonization of the biosphere, can, must, and should put it back. The short-term global carbon cycle is important. That atmosphere at the moment 840 gigaton, increasing about 5 a year. This is coming from fossil fuel, about 10. Those who think fossil fuel running out, we still have 4,000 crude on reserve. That was before the fracking part. The atmosphere absorbs about 123, that's the gross primary productivity, plant respiration 60, the net consumption Uptake by biota is about 60 that get transferred in the soil, respired back by soil respiration. Accelerated erosion is never accounted for in IPCC, contributes 1 billion ton of carbon in the atmosphere. Stop erosion. But 0.6 taken into the ocean obviously is buried. So we can actually look at this global carbon cycle. This is global. We can do it at landscape level, national level, international, regional, county, farm level, or even your plot experiments. Calculate the mean residence time, which is pool over flux, and evaluate how long does that carbon stays. So the total emissions so far, land use 486, prehistoric about 320, that's data of Ruddiman. 1750 to 2010, we know contributed 136, 2010 to 2030, another 30. So 500 gigaton is emitted in the atmosphere over the historic time of agriculture. Fossil fuel compared to that is 400, and much more accurate information. But between now and 2030, the number is going to go very high. And the point that I like to make here is that the emissions from the biosphere, that 486, affects food, feed, fiber, fuel, and shelter, because we lose it. The cause of superinterglaciation indeed is that emission. The soil degradation I mentioned already. I do not know why we cannot apply the Hubert curve to this process. That means the concept of peak soil should be considered. Suitable arable agricultural land under normal conditions should be 0.25 hectare under good management system. But when that becomes less than 0.05 hectare per capita, which is true in many countries, including Bangladesh, for example, that's when the problem of land grab happens. And I do not need to explain what that means. That also causes soil refugees. So the question of endangered soils, not only just endangered species, soil, indeed the organic soils are endangered soils. You cultivate them, you lose 1 inch a year by decomposition. The global food insecurity, we certainly have made progress from about 1990 to now. The curve is going in the right direction, from more than 1,000 billion people to now at the moment of about 800 million. That's the most recent information from FAO. Out of this, South Asia is a very large part, 35%, Sub-Saharan Africa about 27%, Eastern Asia, of course, including United States, and yesterday we heard even Canada, the food insecurity. In the United States, Ohio, 1 in 7 is food insecurity. It's a different kind of issue, but the important part here is the 2 billion number. That the micronutrient deficiencies, 17 essential micronutrients, they must come from a good soil, not necessarily from a pill. So the malnutrition security is very important. The Millennium Development Goal, reducing hunger to 410 million by 2015, unfortunately were not met. If we were to achieve the food security, the cereal yield average of 3.3 tons per hectare by 2025 must be 3.6, by 2050 4.3. That's the total production of cereal on the right-hand side, going from 2.2 billion tons to about 3.3. But if the diet does not change, but yesterday brought up many times, if the diet changes, the yield has to be 4.4 by 2025 and 6 by 2050, and the total production also much higher. So diet has obviously quite a lot to do with it. Now here is a point which is very important. 38% of the Earth's terrestrial surface is used for agriculture. 75% of agricultural land is allocated to raising animals, 3.7 billion hectares. 70% of the global freshwater withdrawals are used for irrigation. 30 to 35% of the total greenhouse gas emissions are contributed by agriculture, and yet 1 in 7 is hungry. 2 to 3 in 7 are malnourished. Something is absolutely wrong in spite of all that resources. So how do you meet the food demands? Some of it was discussed yesterday. We apparently produce enough food already for feeding more than 10 billion people. So what should we do? Reduce waste. The very first speaker mentioned, Ruth mentioned that. increase access to food, that was also mentioned yesterday, address the poverty, distribution, war, political instability, the refugee problems, improve distribution, obviously important part, increasing use of plant-based diet. I would prefer petri dish hamburger if that tastes well, I have no idea. Alternate source of proteins, why not insect? Accept personal responsibility. Wasting food is a crime against nature. Does not matter how you look at it. Order in a restaurant and you don't eat it, must pay for that order, double it. Increase economic productivity from existing land, restore degraded lands, enhance biological nitrogen fixation, convert some land back to nature conservancy, not increase the land, through sustainable intensification and restoration of soil health. I think that is the philosophy. Put land back to nature. There is no reason why sub-Saharan Africa cannot triple the yields. We know how. The technology is there. Yesterday I did ask a question to Ruth, how? I think the political will and political stability are the serious issues that need to be addressed. No additional appropriation of land, water, resources, absolutely not. No justification, none whatsoever. Through sustainable intensification. What does that mean? Produce more from less land. Produce more per drop of water. More per unit input of fertilizer and pesticide. More per unit of energy. And of course, more per unit of carbon emission. We must make agriculture carbon neutral soon. It can be done, should be done. And that's where you reduce the input. That's where you increase the efficiency. The fertilizer nitrogen used yesterday, figure 15 to 50%. If there's no carbon in the soil, how will that hold on to the nitrogen? So produce more from less. What is sustainable soil management? Replace what is removed. I don't care how, I don't want to get into that debate, but replace it, does not matter how. Get it done, respond widely to what is changed, and predict what will happen from the anthropogenic emissions. Enhance soil resilience. Soil's ability to bounce back is very critical, very important. So let's talk about soil carbon sequestration for a minute. When we begin from a prairie or from a forest land, convert it to agriculture, within a few years in temperate climate, 50 years at IITA, it took only 5 years to bring the carbon down to 50%. 5 years in Ibadan, 50 years in Midwest United States. If the soil erosion continues, carbon keeps depleting. If soil erosion stops, it reaches an equilibrium. At some point, if you adopt and improve technology, soil carbon reaches another equilibrium. They call it attainable potential after perhaps 25 years. You improve technology further, including biotechnology. I don't see why not. You can probably achieve a maximum potential with the original level. In some cases, you can go beyond that through innovation. It's really the slope of that line, delta y over delta x, that we need to calculate, which is the rate of change. And that rate of change is what centers like mine do. When you convert to another land use and you adopt best management practices, how do you get, what is the carbon sink capacity of the land? How much did you lose? How much can you put back? That's the part which we need to assess. What is the mean residence time of the carbon when it's put in there? How long it stays? If it doesn't stay very long, what's the idea of putting it back? It doesn't do any good. And then the question is, how can you achieve it? There is no one single problem. There were 300,000 soil series. To assume that there's a one technology that can be adopted on all those 300,000 series, that's kind of being naive. Conservation agriculture, biochar, might be agroforestry, alley cropping, desertification control, drip sub-irrigation, afforestation, pasture management, water harvesting, drip sub-irrigation, improved farming, so anything, site-specific thing. What is the most sacred about it is that the carbon input into the system must exceed the output. Doesn't matter how. But that's the idea, that's the science. And each of those technology has their own carbon footprint. You must account for it. That's the only way you can get the net carbon emission. And that is sequestration is what of soil health is a very important part. We have Dr. Steve Schaefer here who will probably talk about it, which is the physical health, which is water and other characteristics, the chemical health, including nutrient dynamics and nutrient retention, the biological biodiversity of the soil, especially microbial biodiversity, the ecological characteristic, all these processes, the central key factor in the soil organic carbon at critical level, threshold level. That threshold level determines many things in the soil, physicochemical, the biochemical, the ecological, the ecophysiological. It also governs the productivity. Here's an example of soil organic carbon on the stalks, megagram per hectare on the x-axis, the yield from the pampas of the wheat in South America. And there is a threshold level. That threshold level in most soil is 1.5 to 2% in the root zone. You know what the carbon concentration of soils in Punjab is, both sides of the border? 0.01%. You know, soils of IITA, we start with 3% in 10 years. It came down to 0.1%. Yesterday we had the uptake of nitrogen 15%. If the carbon concentration is soil below the limit and you're dumping, for example, fertilizer and irrigation water, and you assume that the efficiency is going to be greater, not possible. That's the ingredient that keeps the nutrients held together. And if you don't have it, then you have to keep on dumping the chemicals and keep on plowing to improve soil structure and keep on adding water because soil does not have a water holding capacity anymore. You have to have that. We know the crop yield for the same management can go up 100 to 300 kilograms for corn, 20 to 50 for soybean, for every tons of additional carbon in the root zone. We need more data for it. Some of this data actually comes from IITA. Millet yield we can increase up on a global scale. Tremendous improvement can be made in soil quality. Mr. Lafol, French Minister of Agriculture in the front row, gray hairs, visited Ohio State, visited my center about a year ago. He was the one who proposed at COP21 the Cather per mill, 0.4% increase in carbon in soil. It's the people like that, policymaker, who translate science into action. That's what's holding sub-Saharan Africa back. That's what holding. I must indicate also that not only the average national average yield I'm talking about in sub-Saharan Africa, low, in the rain-fed agriculture in South Asia and Central Asia, the same thing. It's not made progress. The progress has gone in irrigated agriculture. This is what the gentleman here is proposed for. He said, how much carbon can we put back in the soil? And that's a very important policy issue. He tried to offset oil by soil carbon sequestration. And the reason 0.4% he came is the carbon pool in the root zone, 45, and about 850 gigaton on a global scale. 0.4% is 3.6 gigaton. That was the number a policymaker needed, because over the last 10 years, the average increase in carbon in the atmosphere is about 3.5, 3.6 gigaton. So that's where he came up with the 0.4%. I hope it will be implemented at COP22. Mulching is one of the options. Very important option for soil health, because it affects the soil physical qualities, it affects chemical quality, it impacts biological quality, it impacts ecological quality. The many processes, ecosystem services, the physicochemical, biological processes, soil structure especially, the elemental transformation, the rhizospheric processes, many things really depends on that mulch. Here's a picture from IITA. Many people think, when did IITA soil conservation experiments start? This picture in 1972. Cowpeas grown after corn. I had these experiments on a continuous basis for 17 years. We showed that erosion is practically zero in a system like this, up to 20% slope. But can you keep the carbon, can you keep that crop residue? That's the question. What are the socioeconomic conditions that a farmer under competing uses to feed it to the cattle, to build on fences and roofs and many other purposes, most important, fuel, cooking. How can you convince farmers that this is important? Unless you provide those other amenities to the farmers, the crop residue living on the land is not an option. Even in Punjab, 70% of the price of the grains is the price of the residue of wheat as a fodder. And you ask farmer to leave it back on the land, he thinks you're crazy. Unless you pay for the ecosystem services for carbon sequestration, Mr. Lafol's idea will not work. And what the price of that carbon? Price is not the market price. I'm not against economics. Economics is important. Yesterday, everybody said, especially the so-called ex-politician, he made that point. But it's myopic. It's myopic. Price of at Chicago Climate Exchange of carbon is 10 cents a ton. That's a market demand and supply. The price of carbon, if you take the price of the residue, take nitrogen, phosphorus, sulfur, potassium, to convert that into humus, $120 a ton. And if a farmer sequesters 1/3 of a ton, that's $40 per hectare, $16 per acre. You pay farmers $16 per acre, they do it. Especially the developing countries farmer. Otherwise, no. Otherwise, it's a slogan and nothing more. We also developed at IIT a guideline. Can no-till works everywhere? Well, if you take this climate on one side, you take soil texture on the other side, there is a quadrant where no-till will work. Another quadrant, minimum tillage will work. But somewhere, if there's a humid climate, clay soil, maybe we need some kind of ridge furrow system. So somewhere we have to develop a soil guide. It does not work everywhere. Some place we have to do other things to make it work. But in some cases, it's not a question of it works or not. It reduces 10% yield, so what? 10% yield, but you save 80 tons of topsoil. It's a very important consideration of providing. So how would a future agriculture look like? It certainly have a plan. I had in one of my slides a BT word written on that green leaf. Obviously, conservation agriculture, mixed farming system, nutrients, NPK, zinc. We met a guy from Yara this morning. They should be applied directly to the plant roots when needed, directly. And they should be absorbed in such a way that the nutrient efficiency, they are strictly for plant use and not going back in the atmosphere, not going in the environment. We do not want to do that. And to do that, we really have to have a mixture of setup where we can talk to plants. I would like plant to communicate with me. How? Through molecular-based signals. I would like plant to tell me, look, insect is biting me. Look, I'm thirsty, I'm hungry, I need nitrogen, I need phosphorus. Through the molecular-based signal, I can make intervention timely so that the crop yield is not destroyed. That's the kind of technology we have to have. Of course, we have to have soil biota that create ecosystem services, disease suppressive soils. So a plant has to look something like that. It's not just a crop residue for carbon sequestration. Crop residue requires water, requires, of course, carbon from biomass, requires nitrogen to convert into humus, phosphorus, sulfur, this coupled cycling. We have to understand those cycles together. How does intervention through putting imbalanced fertilizers, how about inappropriate irrigation or excessive tillage? How does it influence those coupled cycling? Which is important to understand. Without that, it's very difficult to generate ecosystem services that we are looking for. We should be farming soil for ecosystem services, not necessarily just only for food production. Many people ask me, how do you sequester carbon in soil? It's like a balance. And in a balance, you have gains and losses. If you want to sequester carbon, the gains by any technology, which I mentioned before, must exceed the losses due to erosion, leaching, and decomposition. That's how the carbon sequestration will happen. If your losses are more than the gains, you are having depletion, and that's what's happening most of the time. We are not putting enough carbon to take care of the losses. Here's another picture from IIT. Late Dr. Tony Juo and I set up this experiment in 1970. It was very close to the farm building size. And this was the Alfie soil. It was very flat ground. And we wanted to make sure that we remove away the crop residue that the farmers do. This picture was taken in 87, 17 after, just before I left. Unfortunately, many of these experiments are discontinued. That's a very sad part of it. But the crop was planted the same day, same variety, same fertilizer. The residue was taken away in one case since 71, and the residue is left back in the other case continuously. A few years ago, I saw the same slide with wheat at CIMMYT. I was told, say, this is unique. No, go back to IIT, see it there from the 70s. By that time, the crop yield, I don't need to tell you what the difference is. And that's because the soil in the front is dead. The microbe, the earthworm, the termites, they require food. That crop residue is their food. You take it away for biofuel production for 1,000 billion tons cellulosic ethanol idea that we have for the USDA, well, there's a price to pay. There's no such thing as a free biofuel from crop residue. Not at all, because soil biota is the bio-engine of the earth. And if you take away the crop residue indiscriminately, you pay a price. Here's another example of taking away the indiscriminate crop residue, the atmospheric brown cloud. I do not need to tell you what the impact on the health of the children, the mothers and baby which is unborn of this kind of situation is. We need to, if the soil degradation is to be reversed, this is where the action begins. Provide clean cooking fuel to the household families in the rural areas everywhere in Africa and Asia. Plant nutrients in India burnt in dung in cooking are more than the amount of chemical fertilizers used. And even then, when you put the chemical fertilizer and there's no organic matter in the soil, 0.01%, they don't stay there. Extractive farming, when you do not replace what you remove, when you do not improve the organic carbon content, you begin with a good soil, you deplete soil organic carbon, you deplete soil structure, it leads loss of resilience, decline in ecosystem services and function, leads loss of biodiversity, microbes, as I showed you in that plot, and eventually that's what gives you hunger, malnutrition, political unrest, Boko Haram, civil strife, war and insecurity, the migrant crisis, the vicious cycle you never get out of. Think again. Soil health is the foundation on which you rest. And you take away that foundation, everything else is empty. Urban agriculture is something very important. Look at the population of New Delhi, went from 1.4 to 20 by a factor of 20. Calcutta, factor of 5. Bombay by factor of 9. Pune, Hyderabad, Bangalore, increasing tremendously. Number of cities, urbanization, very rapid. Look at the cities in Africa, Accra, gone by factor of 3, Addis. This is what is happening in Punjab. The topsoil, 1 meter of it, used for brick making. In a region, no stones, of course it's alluvial, no forest left to build for the timber houses. The top 1 meter of soil used for brick making. Something that took 1 million years, all that organic matter, all those micronutrients gone. You're putting in a subsoil 1 meter deep, fertilizer nitrogen only sometime because it's subsidized, and think that what you're going to grow out of it and eat is nutritious. It's devoid of all the mineral elements, micronutrients. So let's think about urbanization. It takes 40,000 hectares to provide accommodation infrastructure to 1 million people. We are increasing a rate of 75 million per year. That's 3 million hectares of prime land going into urbanization. Cities of 10 million or more are 28 in 2015, there will be 41 in 2030. A city of 10 million people requires 6,000 tons of food. Remember the amount of nutrients, especially phosphorus, going into the city, not going into the back where the land came from, become liability. We really got to stop that. We got to have produced 20 to 25% of the food grown in the city by recycling the nutrient, feeding the cities. That's the planning we got to have. 70% of the people will live in urban centers. That's the only way to do that. So, how do you summarize what to do about soil management, sustainable soil management? First of all, we should think about causes of soil degradation. The biophysical process of soil degradation is driven by economic, social, and political forces. We know how erosion happens. We know how compaction salinization happens. We cannot implement them in sub-Saharan Africa because of the problem of political, social, and economic situation. They need to be addressed. Vulnerability of degradation depends on how, rather than on what is grown, how you grow something. The law number 2, when people are poverty-stricken, desperate, and hungry, they pass on their suffering to the land, period. You call a hungry people and say, don't cut that tree, forget it. Don't burn that dung, or how are they going to cook? I think that's the part which is very important to remember. First, take care of the basic necessities. And then it's not possible to take out of a soil more than what is put in. It's like a bank account. You cannot keep withdrawing without putting into it. Only by replacing what is taken can a soil be kept fertile, productive, and responsive to management. Law number 4, I'm not an economist, but I strongly believe what I said here. Marginal soils cultivated marginal inputs produce marginal yields and support marginal living. And that's the way it is. Good soils cultivated by good methods produce good yields and support good life and stable life. And take care of the soils wherever you're worried about political instability. Law number 5, organic and inorganic. I think it's a futile debate. I really think it's absolutely no question organic agriculture is better. The question of logistics. Can you provide those logistics enough to meet those needs? Plants cannot differentiate the nutrient supply where they come from. The strategies of producing more from less. As long as you can produce from more from less, I don't care how you do it. Combination of both. Mining carbon has the same effect on global warming, whether it's coming through burning organic matter in soil, extractive farming, or fossil fuel, or draining peatlands. Atmosphere impact is the same. And soil can be a source of sink, depend on how you manage it. Law number 7, the potential of elite varieties can never be realized. I want to repeat that. I have absolutely nothing wrong against varieties. They are the greatest thing to have. But remember, you cannot grow varieties in sand system like we are doing in Punjab, or you try to grow in a cemented rock, which I showed you the picture. Their potential, if you want to realize it, they have to have a great media to grow into it. That's very important. Even the elite varieties cannot extract water and nutrients in soil where they do not exist. I heard yesterday about drought corn. I agree there is a drought corn. I knew that. It was called sorghum. Soil has a sink for atmospheric carbon. It's very important part for mitigating global warming. And of course, sustainable management soil, the engine of economic development, political stability, and transformation of rural community. Traditional knowledge, absolutely important. Develop on it. Don't throw it away. But remember, please, today's diseases cannot be cured by yesterday's medicine. Build upon it. It's not either or question. Combine the two together. So just very quickly, Mr. Chairman, I'm coming close to the end. 1715 to 1850, we had hand tools. We had about 1 billion people, less than that. Crop yields about 1 ton per hectare. I'm talking about the Midwest United States here. Many countries in developing countries are still there. In fact, most of them, whether South Asia, Sub-Saharan Africa, are still there at that point, where blue and yellow meet. 1850 to 1950, the animal power came in. The rotations came in. We went up to 4 tons per hectare. People population of 2 billion. Then came the green revolution, fertilizer, machine power, the germplasm improvement, improved variety, the dwarf varieties. The population got up to 4 million. The yield came up to about 7 tons per hectare. From 1750 to 2000, we went up to improved varieties, biological biotechnology came in, the conservation, no-till farming, integrated nutrient management, integrated pest management. We're going to hear about push-pull things soon. Carbon sequestration, we started. Our center began somewhere in the 90s. We got a population about 6 billion. We got yield of about 10,000. Then came about 2000, 2015, conservation agriculture, micro-irrigation, precision farming, perennial culture, complex rotation, and that's where we are. The question is, what's next? I have no clue. I think your guess is better than mine, but this is what I guess. Sustainable intensification, rhizospheric processes, disease-suppressive soils, soil-less culture. Soil is too good to waste just for one thing. Preserve it, see if we can grow without soil. The nexus approach, interconnectivity, the phytobiome management, the Petri dish wheel, the insect alternate source of protein, the agriculture robots, smartphone, producing communication technology. Then what happens from 2025 to 2015? Guesswork, recarbonization of the biosphere. Remember I said 500 gigaton of carbon gone. Farmscaping, insect alternate source, soil microbiome, smartphone extension, soil-less culture, space farming. We are going to have very soon people going to Mars. Do we know how soil processes function under hypogravity systems? NASA is doing experiments, but they're not soil scientists. We need to do beyond agriculture. We need to think about other things. I think we really got to produce more from less of soil. Whatever we do, we got to do. And finally, I'd like to mention soil stewardship. We really have to combine religion with science. And soil stewardship and care must be embedded in every fruit and vegetable eaten, in each grain ground into the bread consumed, in every cup of water used, in every breath of air inhaled, and in every scenic landscape cherished. Thank you for giving me the opportunity to be here.
Thank you, Dr. Lau. We have time for, I think, 2 or 3 questions. If those of you who want to ask questions, go to the microphone in the middle of the room. Yeah.
Go ahead.
Go to the microphone.
Yeah.
Well, so everybody can hear the question.
Yeah, Pierre Herben from Yara. Thank you very much for first an excellent overview of the problems. I liked it very much, and I like also what you say about the degradation, which is okay, a predictable process, which is sometimes irreversible. And you mentioned the point at the moment of in your wheel of the marginal lands with marginal, results. But we believe, I think there is a high potential in regeneration of soils. And I think in your curve on the future, I did not see it, and I think it's important to look at how we can not only avoid degradation, but on the top, starting to regenerate and regain, I would say, soil. The desert, we have seen that in many cases it's reversible, so there are ways really to go back. And I think we need, because there are quite a vast amount of marginal lands, old industrial lands, semi-desertic lands that could really be taken back with the knowledge and the know-how we have in hands. So I think there is also more to do in that reversibility.
I think it's a comment. I agree.
And maybe I wanted to have as well your opinion on that, and see whether you put it in your plan and what you recommend.
I agree that marginal land can be restored. Mm-hmm. I think if we focus on restoring marginal land and put them back for nature conservancy, that would be a great idea. That means prime land should be managed more properly, considering some of the concepts that I explained. So I think that's certainly a good idea. Balanced nutrient is important. I do not want to emphasize that it has to be just chemicals. Integrated nutrient management. That means recycling, compost, biological nitrogen fixation, and supplemented above that, whatever is missing through synthetic fertilizer. One thing I did not mention, and I would have liked to do that, 1 kilogram of nitrogen fertilizer by Haber-Bosch process for its manufacture, for its packing, transport, injection into the ground, cost about 2 kilograms of carbon emitted into the atmosphere. We really have to think about it. Same thing about pesticides and herbicides. 1 kilogram of active ingredient is about 5 to 6 kilograms of carbon. So minimizing them by increasing efficiency is very important.
Yeah, that's a challenge, but there is as well some potential routes for the future to address that.
Yes,
so fully agree.
Certainly.
Okay, we have time for one more question.
I'm a conventional agrologist from Germany, and I had quite a bit of education in soil science. I really appreciate and really like your presentation. I have also a great interest in plant genetics. So I'm looking at the Midwest United States agriculture system growing, well, corn after corn after corn, and sometimes corn after soybean. I would like to see your view on the sustainability of the system.
Thank you. I was a graduate student in '65 at Ohio State, and this rotation farming system was corn, soybean, meadow, pastures. Cattle were a very important component of that. I came back in '87 as a faculty member, and Dr. Fred Miller, some of you may remember him, was department head at that time. And I asked Fred, what is the most prominent farming system now, 20 years after I come back? He said the current system is corn, soybean, Florida. That's the problem. I wish that was not the case.
Okay,
Okay, just got a quick question. I know you mentioned kind of urban farming, and so I'm just kind of wondering what your thoughts are on vertical farming and in a controlled environment and building upward to reduce the amount of space required. I'm just wondering if that's something you see going forward as a sustainable method for producing food, or what your thoughts are on that.
I had a slide on vertical farming, took it out, Chicago, Singapore, have some of those things start. I think vertical farming is going to be a definitely component of producing 20-25% of the food to feed the cities, and recycling waste. You know, when you ask children where the food come from, grocery store, that might come to be true because a grocery store may have aquaculture and upstairs greenhouse structure to grow things. I think that's a great future. I'm editing a book with Bobby Stewart coming out very soon, sometime this year. There's a specific chapter on vertical farming. Everything is on the table.
Okay, please join me in thanking Dr. Lau. Our next speaker is Dr. John Pickett. Dr. Pickett is the Michael Elliott Distinguished Research Fellow at Rothamsted Research in the UK. Dr. Pickett is also a Fellow of the Royal Society of London and the National Academy of Sciences in the US as a Foreign Associate. Dr. Pickett contributes to chemical ecology research. He's still very much involved with such activities in the UK and around the world. He has over 500 publications and patents. His scientific work has been acknowledged with several international prizes and appointments. He has been very involved in research and development in the continent of Africa. He has been the board chair of ISIPI in Nairobi, and he's presently a board member of IITA. His presentation this morning will be new approaches to exploiting plant secondary metabolism, induction of defense and production. Please join me in welcoming Dr. Pickett to the podium. John.
Thank you, Bruce, and a great thanks to Maurice Maloney, but not just Maurice, to the scientists, the business community, because it's largely agricultural, and the politicians of this province. What a wonderful place to have a meeting like this. My talk, as you can see, relates to some technical issues, but it really tries to tackle some of the challenges that were laid down in the report by David Bulcombe and other colleagues in the UK, Sustainable Intensification of Agriculture, to which Maurice referred in his opening remarks. It also tries to flesh out, I think, some of the technologies that we should strive for that are the obvious extension of that wonderfully inspiring talk we've just heard from Ratan Lal. Secondary metabolism is very cheap. That's why it's secondary. And so you can do things to it that don't mess up the phenotype of your agronomically advanced elite variety of crop. And I'd like to offer it as a target for some of the new techniques that we have now in molecular biology, and not least genome editing. Just about a couple of weeks ago, less than a couple of weeks ago, I had a comment in Nature Plants. The reason for my being invited to make that comment, slightly sad scientifically, and I'll refer to them at the end of my talk, but the title was in fact the essential need for GM crops. And as you can gather, I didn't take part in the discussion yesterday, but that probably says where I would be. And I think Sarah Gurr, in her comments herself, referred to my views. But I sneaked into that comment this diagram, and it really relates to the extension of the science proposed in the Balkan report, in which the crop has to really look after itself in many, many more ways than it does at the moment if we are to have sustainable intensification truly occurring in agriculture. We're going to have to make only one pass through the crop, and that is to take the harvest. We're going to have no seasonal inputs at all. That means we have to perennialize, and the plants have to do everything else themselves. This is a very, very long way away, but we won't get there without the current tools, and I hope new tools that will emerge from the rapidly advancing subject of plant molecular genetics. So in that envisaged scenario, we have a sparse number of sentinel plants that really manage the crop in terms of being susceptible to pests and diseases, noting problems of drought, insufficient nutrient, but also responding to positive advantages, and by signaling, using through the rhizosphere or through the air, as in this example, secondary metabolite-based chemical signals, get the main stand of the crop to do what it needs to do. This is beyond unmanned aerial vehicles, beyond long-range surveillance, and entering into tactical and decision support-based delivery of inputs. And it's fictional at the moment, but it's where we have to kind of aim some of our science, I believe. Let me not repeat what Gary Stacey did so brilliantly yesterday, but refer a little bit to some of the problems. And I've chosen a way of doing this which is slightly provocative, because it relates to the fact that nobody knows what this piece of iron is. I stood, having been completely immobilized by a torn ligament operation by this Haber-Bosch reactor in Frankfurt, asking not just scientists but chemists what it was, and they didn't know. I couldn't find anybody who knew. There was even a plaque there, as you can see, saying what it is. It's a truly magnificent piece of chemical engineering, but there are literature examples explaining that 80% of your bodily nitrogen has been through such a reactor. And it's credit to people like Pierre Harbin and Yara that that can be possible, because we'd certainly be starving big time if it weren't for that at the moment. But it's a tremendous drain on our resources, and it has to be delivered to the land. But there are many, many other inputs, and Ratan Lal really explained that very nicely to you. We're quite wasteful of some of this, and the more we strive for increased yields, then the more we will find we are wasting. But we're not just wasting, we are releasing nitrous oxide, an extremely powerful greenhouse gas. Rothamsted's well known for its classical experiments running since 1843. There's John Bennett Laws, the guy who started it all. And, you know, we have aspirations to do more of this. The Green Revolution has got a lot to offer still, but we need a new technological revolution. And Norman Borlaug himself was very quick to point that out in his last years. We made a film with Norman at Rothamsted, and there you can see him. And sadly, I don't have a full picture from the film of the other part of the conversation, but it was a few very idealistic early career postdocs who were challenging Norman that we didn't need GM, basically. And there is one of his well-known quotes saying that we don't have to have that option, really. So I'm going to talk about plant signaling. I'm going to talk about chemicals that are produced by plants when they're damaged, or from particular taxonomic examples of plants that signal to intact plants to do things. Predominantly, I'll talk about defense, because that's the area that I work in mostly, but they can also stimulate growth, provided obviously that the nutrients, the water and the photosynthate is not limiting. Some of the defense that they bring into being is also a set of signaling compounds. And I work on insects predominantly, but this works just as well for antagonistic weeds and for pathogens. And some of those signals that I'm going to talk about are there. So the elicitors are in the middle, and then coming out of the plant are two types of signals. They're called homoterpenes because they have an extra carbon, and a compound which is actually a pheromone. But they have the role of warning away herbivores and attracting in beneficial insects, which we have an extremely large global population of, and they can be enhanced by ecosystem services. And it's not just pollinators we have to think about. Now, my inspiration for this has come from the work to which, again, Maurice Maloney alluded yesterday, with my good friend and colleague Zia Khan, based in Kenya with ICIPI. Now, I could have had a picture there of one other person, but he's in the audience, actually, Richard Flavell, Dick Flavell. When he was director of the John Innes Institute, which he did a spectacular job of, he was asked by the Gatsby Charitable Foundation to look at ways of using elite science in the UK in a way that would alleviate poverty, particularly rural poverty in Africa. And I was already working with ICP under the towering and charismatic figure of Thomas Odiambo, you see there, on mosquito control, in fact, when in the early 90s we joined forces with Zia Khan, who had recently been recruited from IRI and who will be speaking later on today, to look at ways of managing pest habitats to control them. And out of that came the push-pull, or in Kiswahili, vuta sukuma, which I know is pull-push. And what it comprises is a very intensive, a very knowledge-intensive process of using companion crops. And Zia will explain this in more detail, but I need a few tricks that we've learned from it to explain my cause today. And with these companion plants, which are perennials and are extremely valuable as cattle forage, you create a push and pull. You attract in natural enemies, you push out the moths, and you get the moths to lay their eggs and procreate initially on the trap crop, which you feed to animals, to farm animals. They eat the protein, they destroy the pests, they reduce the population after you've moved it around with these semiochemical cues related to the pheromones, but which are only used by insects or animals or plants, indeed, of the same species. Now, the crucial chemistry turned out to be one of these homoterpenes, this compound here, we'll call it DMTD. And we published it soon after starting the work, which was intended to be on farm from the outset. In fact, we had to struggle to get some money back into the project to find out really what we'd achieved with an empirical version of push-pull. And we even published it in Nature a couple of years after we started what was a purely development project, but based on the push-pull concept. We've since found that when some plants detect eggs being laid on them by pests, then the plant starts to produce these homoterpenes, and they repel pests, but they also attract in beneficial insects to attack the eggs, of course, egg parasitoids, but also in anticipation, and hence the term SMART, in anticipation of the eggs hatching into larvae. But it's not any old plant that does this. It's a largely unimproved landrace type plant, or an OPV, an open pollinated variety. It's absent from all of the hybrids we've looked at in a very, very large survey, except for one, which was developed in Zimbabwe for low input agriculture. So the plants themselves were left with resistance. They weren't protected as you would normally do in a breeding program against insects. Now, of course, the genetics for that is extremely exciting because it's an inducible signaling system that is potentially extremely valuable. Now, there's a lot of talk about unconscious bias in the UK, and we're all victims of it. And your unconscious bias will immediately tell you that the guy standing in front there, prominently in the blue shirt, is the farmer. But he's not, of course. It's the lady behind him who's the farmer. We're very proud that we have a very high gender balance in the push-pull program. They are technologies that women can use and identify with very, very well. And she has been keeping one of the local OPVs called Nyamula, and that's it growing there. And it's really very, very good at this signaling. So wouldn't it be nice to capture that? So with all those august funding agencies, we've got a big grant with, you can see there, Ed Buckler, the maize geneticist from Cornell, and Damaris Odini from ICRASAT there. And we've been trying to do what I would consider to be relatively conventional genome-wide associative studies. And of course, it's not really going very well, because what we're talking about is an induced effect. All these plants, they're all different in all kinds of ways that have this trait. The OPVs, the landraces, the teosintase, which do it really very, very well. But they're all amazingly genetically different. So your GWAS produces all kinds of false hits when you're looking for the inducible process. But when the eggs are laid on the plant then, and the plant detects it, if you just peel back that little egg raft of Chiloportellus, there's something underneath it. And that's mostly to do with holding the eggs on the plant. But in there is something that goes through the intact plant cuticle and systemically calls into play defense chemistry. When I left the chairmanship of the Governing Council of ECP, I was delighted and extremely proud to have caused the appointment of Seganet Kalimo to be the new CEO of ECP. And she is a plant scientist and knows full well what tricks we can do if we've got an inducible process. Now, the chemistry of that egg glue is mostly lipoidal, but it's not compounds like POP that do the trick, of course. But we have got in bioassay in Kenya at the field station at Mbita Point the actual compounds that do it. So now all we have to do is put those onto one of our varieties, perhaps the 1 hybrid, since it grows very uniformly, to see by RNA-seq, using next-generation sequencing, obviously, as the creator of the raw material for that, which are the induced genes. And we kind of know what they are in terms of the functional ones, because we already know what the chemistry is from our work that I've already mentioned. Now, as the push-pull has developed, we've had a lot of inputs from farmers in terms of what they want it to look like. And we moved over to a legume from various grasses that were fulfilling the push role. And there is Desmodium uncinatum, grown, as I said, as a perennial with a trap crop, in this case, Pennisetum purpureum or Napier grass. And into that we grow the annual cereal, sorghum or maize. And by chance, whilst we'd been asked if we could do something not just about the insects, but about Striga, particularly Striga hermontheca, we found that we had an extremely impressive control of this weed with the Desmodium species that we're using as the intercrop against the insects. This was purely serendipitous. We wouldn't have noticed it perhaps if we hadn't been doing such very good experiments, but it was very, very clear that we had massive control of Striga, and it's a suicidal germination, the mechanism of which Zia will refer to, which means you get rid of the seed bank. You don't get rid of the seed bank with so-called resistant varieties, because they're not really resistant, they're just tolerant, and that builds the seed bank. Now, we've recently, as Zia will also say, been asked by the European Union and funded by the European Union to create a climate-adapted push-pull, which really means using drought-tolerant push and pull plants. And that's been a wonderful excursion into diversity, to use species diversity within the Desmodium genus to capture other plants that have the insect controlling trait and the striga controlling trait as intercrops, and yet have the ability to resurrect when the rains come and the farmer puts the annual seed into the ground. And one of those there, Desmodium incarnum, I want to refer to particularly because it's my job just to talk about the signaling chemistry that results in this suicidal germination of striga. And there it is. I can't point to the salient bits, but there's a compound top right called isoshafticide. It's got 2 sugars on it, but they're joined to the epigenoin core by carbon. And you have to have special C-glycosyl transferases to do that. We got them all from rice, not that rice resists striga at all, it's extremely susceptible. But that got us to the middle compound. We still needed 1 more sugar on there, and arabinose, C-linked. And the Desmodium incarnum, the new drought-tolerant Desmodium in the program that Zia is leading, just provided that for us. So we have the wherewithal now, potentially, to create an edible legume, but with the striga controlling trait. Edible for us, that is. All these Desmodium species are very edible for cows. The rhizosphere offers a lot of opportunities for signaling. And very recently, we published a wonderful account of a kind of highway that exists in the rhizosphere via the arbuscular mycorrhizal hyphae, and that it allows a very rapid transport of stress signaling from damaged plants to undamaged plants. So here we have a fantastic opportunity to do some of the early sentinel work, as we do with Embrapa at the moment against the Asian soybean rust, Phacopsera pachyrizae, which affects the secondary metabolism in the plant before you can see by molecular genetics or visual appraisal the development of that particular rust. But going back then to exploiting the homoterpenes, we have one other homoterpene. There are actually 2 of them that are players in this game, where n equals 1, the DMNT, and when n equals 2, TMTT. And they're homologous because they're formed by the isoprenoid pathway, and they have 5 carbon atom units in there, but they lose 4 carbons, and so being pedantic chemists, we actually call them tetranorterpenes. They've lost 4 carbons. And we find these compounds coming up with herbivore damage across the plant kingdom to wild plants and all the main crop plants that we have our current interests in. And pretty well all the wasps that look for herbivores have single olfactory neurons that we can record from that are tuned particularly to the higher homolog where n equals 2. So now we've got to try and switch them on then without damaging the plant. So we need small lipophilic molecules, secondary metabolites that switch on these genes for the production of the homoterpenes, but without the aphid sucking on the plant, as you see in that diagram. And we have such a compound. It's related to jasmonate, the plant hormone, but it's an external kind of version of it. It's volatile by merit of having lost the carboxylic acid group. Although it's related to jasmonate, it doesn't signal through the same genes as jasmonate. So it doesn't have the disadvantages, but it has some quite spectacular advantages in terms of switching on defense and also stimulating growth. We can find it in plants damaged. A very, very small amount of it. If chemists were asked to find that, they wouldn't be able to because, you know, by stamp collecting compounds, you don't get there for ages. It's such a little peak. But electrophysiology can help us listen in to what the plants are saying to each other. And that electrophysiological response there picks out that minute peak from damaged potatoes. But we can also switch on production of the DMNTT, not only by putting the aphids on the potatoes as we did there, but by now just putting some of this cis-jasmone in the atmosphere. It's active at a phenomenally low level, milligrams per hectare. Yes, milligrams per hectare. It's extremely difficult to deliver it like that. Hence another reason for thinking of the Sentinel technology, which kind of does it for you. But there have been very extensive industrial investigations in the field of the use of the compound. It won't be developed as an elicitor, but it's going to be developed by us in the process of approaching the Sentinel technology, though the growth-stimulating properties probably will be developed commercially. It works on Arabidopsis, of course, and with Jonathan Napier and Michaela Mathers at Rothamsted, we've been able to look at the genetic cascade that relates to the production and signal detection. And as I said, it doesn't signal through the genes that jasmonate does, and so we see other genes upregulated with cisjasmone, like that cytochrome P450. And I'll go through this quite swiftly, but basically you can show that the same genes, when constitutively upregulated, cause the kind of defense that we get when we stimulate it by the cisjasmone, proving cause and effect. And we can use electrophysiology to find the unbelievably minute amounts of these compounds. Peak 14 is TMTT, but there's an electrophysiological response there in that rather wobbly trace, but it is, after all, from an extremely small wasp, which spends its growing life inside the aphid and kills many hundreds per insect, of course, and represents an extremely important ecosystem service, as I mentioned. But obviously it's the generation of those compounds that we're interested in, and the biosynthesis of cisjasmone, which is also different from jasmonate. It comes in from the oxophytodianoic acid part of the pathway in a very interesting route elaborated in collaboration now with Willy Boland's group at the Max Planck Institute in Jena. So, what can you do with it practically? Well, certainly in simulated trials, we could easily see that parasitic wasps would forage more avidly on wheat. And then we could do a field trial. Now, you see us there typically dressed for a non-registered experimental permit compound. But cisjasmone finds its way into Chanel number 5. It's a component of that lovely smell of magnolia flowers. It's in various foods, and it's got generally recognized as safe designation as a food additive, but that's what you have to do. The markers just mark out the plant so we can count aphids. And we can show that many weeks after treating, because it's a switch that switches genes on for defense, we've got a statistically significant control of aphids. We can also show that there are antibiotic effects against the aphids. And what is happening is, in fact, although this pathway to the benzoxazinoids or hydroxamic acids is only vestigial in hexaploid elite wheat varieties, it's upregulated by cisjasmone fairly big time. And that's another defense route that relates to this kind of signaling. It works, as I said, in all the main crops, in cotton. With Indian and Brazilian colleagues, we can see TMTT and DMNT coming up, and an associated reduction in Aphis cassipiae, an aphid, a sucking insect, not a target for Bt endotoxins, and so an augmentation potentially for that kind of insect resistance. Soybean main pests are stink bugs. Stink bugs are parasitized, but the parasites come in late. They want to feed off the hosts that are our pests. We want them in earlier, and with cisjasmone, glycine-max does the job of producing the homoterpenes which attract in the parasitic wasps. With Nigerian colleagues, we've shown that you can prime the plant. You can prime plants with methyl jasmonate and jasmonate, but you get usually erratic results and damage. But with cisjasmone, we get a very nice priming. I've got a slide following with from the Oluwafemi work with Nigeria, as I said, which explains that, but it's a bit complicated. I'm going to whiz over it in the interests of not giving Bruce mental problems as he wonders how I'm going to get through the next 58 slides. So we haven't got the genes quite sorted out for this homoterpene story, But, and we're not the only people not having it sorted out. There's some lovely work in the US not sorting it out quite yet either. It's quite difficult to get control of this pathway and upregulate it in a GM crop. But the other compound that I mentioned in my introductory slide is E-beta-farnesene, which is a pheromone, but it's an alarm pheromone. So when aphids are attacked by a predator, as you see here, they produce this defensive little droplet of sticky material. That's what it really does. It gums up the mouth parts. But at the same time, it releases an extremely small amount of the alarm pheromone, which the aphids, being clonal, they parthenogenetically reproduce, respond to by scuttling off. So while that poor parthenogenetically reproducing female will die, the other ones will survive if they get back onto the plant, having fallen onto the ground. So it repels pests, but it also is a recruitment queue for parasitic wasps and indeed predators like that one there. And in the early 80s, I had the audacity to suggest that one day we could make a transgenic crop that would do this. And I was roundly told that I was at least 10 years ahead of my time. Well, I turned out to be, in fact, 20 years ahead of my time. But we did know that it worked. Just as we know that the homoterpenes work and are a worthy target for GM, we knew that the E-beta-farnesene worked. A very long time ago, when you could publish papers in Nature with only 2 authors, we had this paper showing that certain trichomes on Solanum bethultii could release the pheromone just in the same way that the aphid did. We also knew that if we sprayed E-beta-farnesene protected in the matrix of an essential oil, we could get some kind of control of aphids. It would cost a fortune, but the principle was established. But there was a problem with the genetics, and that is that when plants make E-beta-farnesene, which they do, in fact we all consume it, I particularly because I like real ale with a nice hoppy flavour, then it also produces several other sesquiterpenes, including the isomer of caryophyllene. And the aphids and their predators have acute olfactory ability to detect the presence of the other compound with the E-beta-farnesene. And they use that to know that it's a plant trying to trick it. So we had to engineer either the gene or the way we were going to use it not to produce the other compounds. And crucially, electrophysiology on the aphid antenna and indeed on the predators, where you can see the juxtaposition of those 2 olfactory neurons on the antenna of the 7-spot ladybirds, important predator of aphids, the 2 cells, this high amplitude one for the farnesene and this lower amplitude one for the caryophyllene. And when they both fire, the aphid doesn't have to worry because the ladybird will not be searching. It will associate that with being fooled by a plant. So we had to get away from that, and we did that. And you can see I wasn't just 10 years ahead with this optimistic idea, I was 20 years. It took us that long to publish, and only in Arabidopsis that we could make a transgenic plant that made the E-beta-farnesene pure enough to convince the aphid that it was receiving its own alarm pheromone, and it worked equally well with parasitoids that are willing to catch an aphid on a cruciferous plant. So by that time, we were ready then to do the crop. And in 2012, we got the grant underway, and we decided that these had to be synthetic genes because we got to use codon optimization from the Arabidopsis work anyway into a monocot. So, and we used ubiquitous promoter systems. We got no results at all, as we had so wonderfully done with the Arabidopsis. So we argued that maybe we didn't have enough farnesyl diphosphate, so we put that in as well. And we still didn't get any good results. Only when we actually moved the gene products into the plastid, the powerhouse of the plant, of course, but the organelle in which you do not make sesquiterpenes, which is what E-beta-farnesene is. So counterintuitively, though, that's what we had to do to get both the E-beta-farnesene synthase on its own, but also the E-beta-farnesene synthase with the farnesyl diphosphate synthase. That's what we had to do to get those. So we got now 2 very stable lines of wheat, which generation after generation produce either a large amount of E-beta-farnesene or a small amount of E-beta-farnesene. Now, it took us a long time to publish the field results, which finished in 2013, because we didn't expect there to be a phenotype from making this transgenic wheat, other than the one we'd intended. But in fact, the authors, the reviewers of our paper, didn't believe us. So we had to go back and do a lot of the biology. Fortunately, we got stable lines. But I got all the chemistry samples, and we did find one phenotypic difference. We found this small amount of myrcene. Now, myrcene is an C5 homologue of E-beta-farnesene. And of course, what was happening is, without the farnesyl diphosphate being augmented, the E-beta-farnesene synthase was scavenging anything that looked like the precursor, farnesyl diphosphate. And of course, geranyl diphosphate looks like that. But that doesn't make farnesene, it makes myrcene. So science was not fooled by unexpected happenings there. We could predict what this was. We could find it with the electrophysiology. The aphids weren't interested. The wasps weren't interested in it. But we were able to explain that there was no impediment to photosynthesis, even though we are commandeering the isoprenoid pathway, which makes phytol. And we could prove all this and get the work published. Of course, we'd had to show that it worked in the lab and in field simulation. And we could frighten aphids. We could even do it better than the pure E-beta-farnesene itself. We actually got a bit of help from the plant, which was still elucidating. And we could get the wasps to forage. So in 2012, we were at the position then of starting the field trials. Now, we can do field trials of GM crops in the UK, and we have an august committee that decides whether it's appropriate to allow a license for that. But at the time, we had a number of people that were dedicated to destroying the crop. They told us the day when they were going to come to Rothamsted and destroy it. They had a bit of a field day as well, in all senses, because we'd had to use a non-plant sequence for the farnesyl diphosphate, and we chose to use a bovine sequence. We could have used a human sequence. We thought we're going to use a bird sequence, but we used the both. So they've had a wonderful cartoon of a loaf of bread with a cow's head coming out of it. And we don't mind that. We like the humor. We like engaging. But we had to engage with the majority of people who would have perhaps allowed vandalism to take place. And with help from colleagues who were having a wonderful insight into this process, like Mark Lynham, who gave such a wonderful performance yesterday, we were able to engage with those people who didn't want to eat genes, but nonetheless wanted the experiments to be looked at, because they know that with science, you have to do experiments before you can take it forward. And so we did the experiments peacefully. So we used 6 by 6 meter plots of the high, low, and the low farnesene releasing. We used the control of cadenza, an elite variety at the time, with no other phenotypic differences than the E-beta-farnesene production. We had a buffer of barley, we had a buffer of wheat, we had a great big fence around it so that people didn't take the genes out, they had to be retained there. And eventually we published the results. And many of you will know, and this is really why I was asked to give this comment in Nature, it didn't control aphids. There was a little bit of a sign on the bottom trace that the low level of farnesene release might have done, but it didn't work in terms of control. But it did work in terms of testing a hypothesis. We didn't either manage to get any more parasites into the plots, and it was a very low density. We're repeating the work now at much higher parasitoid densities in the US. We are not using constitutive promoters. The aphid releases the pheromone as a puff. We have the promoter sequences in wheat and various crops based on our original work in Arabidopsis, activated by cis-jasmone, of course. And we also have a bit of a gift in that I'm just going to pass over this. It just relates to cisjasmone and its growth stimulation from industry and the link to the cis-zeatin cytokinins, which can stimulate growth and have an isoprenoid component, to this slide where we have in triticum aestivum then a farnesyl phosphate gene, to our great good fortune, which is massively upregulated very, very early on in the attack by aphids. And this was with colleagues in Beijing at the Genetics Institute there. So that's obviously the way forward. But maybe we shouldn't be using, in our main thrust of this work, a pheromone, an insect pheromone. We will use the aphid sex pheromone, another pheromone that also attracts parasitoids in some work that's running at the moment. But really the main target has got to be these homoterpenes or the tetranorterpenes, and their role demonstrated so wonderfully clearly in the push-pull in Africa, which Ziakam will give you chapter and verse on, and which we believe we will be able to capture with work from our lab on the genetics, which you see there, and Dorothea Toll's lab, which you see there under Li et al. And in fact, we have 2 programs with China targeting Nylopovata lugans, the brown plant hopper, to do just this. And we will, I'm sure, achieve success, certainly staying within the plant secondary metabolites, which is the thesis of the work that I've suggested. So I've abdicated my responsibility for talking about production because I whizzed over the slides where I showed you that cisjasmone and indeed the other elicitors we're working on and that other people are working on cause growth stimulation as well. Just to finish up with the fact that we are dependent upon the Haber-Bosch process. It's great that industry is conscientiously improving that process, and we must make best use of it while we have to do that, while we wait for Gary to give us, and Giles Oldroyd to give us alternatives of real practical value. But in the climate smart push-pull, where we've moved to Brachyaria species, in fact apomictic Brachyaria hybrids, we've got plants like Brachyaria humidicola that produce chemistry that interferes with the nitrification process and reduces nitric oxide. And that's some of the chemistry. And as a chemist, we've putatively put together the biosynthetic pathway so that we can use bioinformatics to capture the operon, as it were, the cluster of genes towards that biosynthetic route, to look at the possibility of getting that into the cereals that we're going to add more Haber-Bosch nitrogen to so that they will produce less of that greenhouse gas while we achieve the longer objective of reducing to zero all inputs except the diesel for harvesting the crop. Thank you.
Thank you very much. We have some time for questions before our break.
So in your proposed system for using plants to attract predators of aphids or what have you, how do you see that working, given the natural population dynamics of both the pathogen or the predator and the problem insects, so the aphids, right? So even in your long-term view of a sustainable system where you have perennialized crops and this system is deployed, I mean, you have an annual variation in the incidence of both the problem insect and the predator. So so one year there might be lots of the problem insect, and then the population, as you showed in your last experiment, the population of the predator isn't adequate, and you have to wait 1 or 2 seasons with a high incidence of the prey.
I take your point. I take your point. You made it very well. I think it's a very important issue. The whole idea of the Sentinel technology is you don't signal to the wasps to come in until you've got this initial attack on the Sentinel plant, which is susceptible by whatever insect it is. I illustrate it for aphids because that's the main insect pest we work on. But in Africa, it's all Lepidopterous insects. And in Africa, the system does it for us. So the plant itself, detecting the damage, signals in for the wasps to come in. And the ecosystem service is already there in Africa. The very diverse fauna and flora that you get in Africa can actually offer great dividends, particularly the flora that relates to looking after very large populations of beneficial insects. Now, clearly, you can't do that in prairie cereal production. You've got to have ecosystem services. I mean, in a recent paper in Nature Climate Change, we said if you're going to have to use sparing land by increasing intensification in agricultural production, then the ecosystem services on that spared land have got to count. They've got to be useful. Now, we can actually regulate the chemistry, the signaling chemistry of wild grasses. We already know we can do this, to actually tell the wasp community that is sitting there happily living on the parasites in the grasses to go. And then we have the pull into the crop with the kind of technology I've talked about when we need it. But you've got to replace the wasps if you're going to do something to them which prevents their population being maintained. And that is part of the payment for ecosystem services. But it's a sustainable system that should manage itself, provided that we've got all this signaling in place. And it's an alternative to insecticides. I'm the Michael Elliott Distinguished Research Fellow. I live in the shadow of deltamethrin. It's a very big shadow that it casts because it's still, with permethrin, the main intervention against malaria. But Michael's dying words were to me, try and do something better. And better is not doing that at all, but having it reserved for firefighting. But we don't use these wasps because of the problems that you have outlined. And that's why we need to create these tools with which to manage, conserve, and make better use of that ecosystem service.
So sorry, just one thing quick. So is there modeling that has been done to establish the ratio of reservoir?
Yes, roll potting is now back in Wageningen. I mean, this area of work in Africa is the most documented development program I think you can imagine. I think they will tell you it's nearly 100 papers, peer-reviewed papers on this, many of them high impacting. And we've done modeling on the whole structure of the push-pull system. And in fact, empirically and with farmers' interactions, we've actually hit upon a very happy model target, but which was got to empirically. But certainly at the moment, we're not seeing any depletion in the ecosystem services relating to wasp production. It was really a target that has to be looked at for when you've got monoculture use of this delivered by the kind of technology that I'm talking about, but also, what should we say, perhaps over-optimistically predicting for the future.
So what would be the typical ratio of land for reserve versus production?
Well, any kind of land that you put to ecosystem services is questioned if you are still not producing enough food. But if you intensify agriculture, but use that to spare some amenity land or ecosystem service land, then you can make it fix. And it depends on the system and the crop and everything. But in this paper that's just a few months out in Nature Climate Change, you'll see some very stark statistics saying that sparing can actually pay, and provided that the ecosystem service itself pays.
Okay, please join me in thanking Dr. Okay, we'll go on our break now, and so the next plenary session starts at